Okay, so to update on the crystals have grown significantly, as you can see. They kind of layer the entire bottom of the vial at this point. Um, but yeah, they've grown significantly, and many different sites of nucleation have formed crystals. Although the formation was relatively slow, such numerous sites of crystal formation indicate that the level of purity of these crystals is not extremely high. There has been one environmental factor that could have influenced the crystal growth recently, and that is the weather has warmed up significantly over the last couple weeks. This could have an effect on the growth of the crystals, in the sense that a higher temperature could yield faster rates of evaporation, which would make the crystals likely more sparse and separated different sites of nucleation as well as more impure. Um, so improving on this experiment in order to grow more pure and larger crystals, I would first obtain a supersaturated solution of alum like we did in this experiment. Next, although it's important to have or to avoid having too many nucleation sites, which form smaller crystals, either solvent evaporates or due to vibrations or other disturbances. But a good way to ensure this result would be to start with a seed crystal that is suspended in the solution. So maybe on a string from the lid of the vial or something along those lines. But the seed would provide an ideal base for the newly formed alum crystals, so that they can grow into pure structures. So either like one of these small crystals that I have here, or maybe a more pure, smaller crystal to start, to serve as a nucleation site for more pure crystal growth. But lastly, crystals that grow more slowly tend to be larger. And so this is because if the solvent evaporates too rapidly, many alum crystals will form in a short period of time with more impurities. So to achieve this result, I would just place another layer of Chem Wipe or two on top of the vial in order to slow the evaporation process, and slow the rate of growth of the crystal. In turn, the crystal would be larger, and more pure. Compared to my results, this would ideally be one large and more pure crystal instead of smaller, moderately pure, but more bountiful crystal formation. And so when we're analyzing crystal structures, one important concept is despacing. And despacing is the first step when doing X-ray crystallography. The repetition of periodic arrangements of atoms in crystals lets us identify many sets of parallel planes of atoms. And for each set of parallel planes and these structures, there's a consistent distance between neighboring planes. And this is the despacing. So when X-rays approach crystal planes, the waves bounce off different planes, and for this reason, they can either be in or out of phase and have potentially different path lengths. So the angle theta at which the X-rays come in forms a triangle with one of the legs equal to 1/2 the path length difference, and the hypotenuse equal to the distance between neighboring planes, the despacing. Therefore, we get the formula. Formulas n, which is the order of reflection, and that's either an integer from like 1 to 4 usually. It's typically 1 though. So we have n times the wavelength equals 2 times the despacing times the sine of theta. And so in powder diffraction experiments, a graph of 2 theta versus intensity of diffracted light gives a unique pattern depending on the structure, and the peaks are caused by various unique sets of planes. And so with all this information, one can completely define a crystal structure, and this was all originally enabled by the existence of these consistencies in despacing. So in this way, despacing is the fingerprint of a crystal structure. So, using powdered X-ray data, we can calculate the despacing. And so here we have the graph shows that the highest peak is at about an x-coordinate of 2 theta equals 21 degrees, giving us a theta value of 10.5 degrees. The wavelength is also listed at 0.15418 nanometers, and we assume n to be 1, which it typically is. So plugging all these values into the equation, right here, we get the value 4.23 angstrom, or 4.23 times 10 to the negative 10th.